Awesome. Well, thank you all for thank you to the organizers for inviting me, and thank you for hearing me out to talk about this project that I did with two people. And so these are my collaborators on this project. On the left is Matthias Beck, who's. Do y'all hear the train? Do you all hear the train? Every single time without fail that I give a talk on Zoom in my apartment, the train passes. Oh, okay, well, it'll be out of the out of the thing soon. But in any case, on the left here we have Matthias Beck, who's a professor at FS State and who's currently at FU Berlin. And on the right is Ben Braun, who's my PhD advisor at the University of Kentucky. And because when you're funded by the NSF, you should say that you have that money. So was funded by the NSF. But anyways, the main characters of my story are polytopes. And so I feel most of you are probably familiar with polytopes, but I don't want to assume anything. So I'll just say, I'm going to take V to be a vector space. And I'm going to take so what is a polytope in a vector space? Well, one definition is it's a bounded intersection of finitely many closed affine half spaces. Another definition is that it's the convex hull of finitely many points. And so here is an example of a hexagon as a bounded intersection of half spaces. And here is that same hexagon as the convex hull of 6 vertices. And so I'm going to take a lattice. And so I'm going to take lambda to be a lattice. And for me, I really do care about the integer lattice. So I'm really thinking the integer lattice. And so we say a polytope is a lattice polytope if all its vertices are points of the lattice, okay? And I should say, I can't see the chat, so maybe Theo, if you can like interrupt if somebody puts something in, but please make or interrupt me if you want to speak out loud and just ask questions along the way.
Sure, I'll do that.
Awesome. And so, again, maybe Ehrhart theory is something that you might be familiar with, something that you might not, but Ehrhart theory is essentially the study of counting lattice points in dilations of polytopes. So again, I'm giving a d-dimensional lattice polytopes in a vector space. And so we define this lattice point enumerator where we're just counting the number of lattice points in dilations of the polytope. And that's this T, the T dilate for some integral dilate, okay? And so a result by Eugene Ehrhart from the 1960s says that this lattice polytope really corresponds to a polynomial of degree D. And as combinatorialists, we like to encode things in generating functions. So we're going to encode that lattice point enumerator in a generating function. And so then we get it to be this nice rational form. And some of you who might be more familiar with algebra, commutative algebra, might say like, oh, that reminds me of a Hilbert series. And so it's because the Ehrhart series is in fact a Hilbert series of a graded algebra. And when we have it in this nice rational form, we call this numerator the H star polynomial, or the numerator is the polynomial, and it's the H star, we call it the H star polynomial of the polytope. And it's a polynomial of degree less than or equal to D with non-negative coefficients. Oops, what did I do? And so here's maybe a small example in the lattice case. I'm just taking the unit square and I'm dilating it. And so the lattice point enumerator, it's not that difficult in this small example to see that it is given by a polynomial and it's t plus 1 squared. And so when we encode it in the numerator, we get 1 plus d as our H star polynomial. And so there are plenty of open questions about H star polynomials and things like this. And so one big question in Ehrhart theory is, can you classify all Ehrhart polynomials or equivalently all H star polynomials? And what I mean by that, if you give me a polynomial, I can tell you the polytope that it belongs to as an Ehrhart polynomial. The answer is we don't know that for anything higher than dimension 3. So it kind of speaks to the difficulty of that problem. And so I care about, or for this project, cared about rational polytopes. And so these are sometimes the forgotten siblings of lattice polytopes, but there's plenty of things to do for rational polytope. So I'm given a d-dimensional polytope in R to the n with rational vertices. And so actually Ehrhart proved something stronger, and he said his result holds for rational polytope. So it turns out that the counting function L sub p of t is in fact a quasi-polynomial of this following form, where these k sub I are periodic functions in t. And we call this the Ehrhart quasi-polynomial, where each period of these functions divides the denominator q of p. And so I'm defining the denominator q associated to my polytope p to be the least common multiple of all its vertex coordinate denominators. I'll repeat that again because it was a mouthful. The denominator q of p is the least common multiple of all its vertex coordinate denominators. And so there might be some questions here that I'll ask, and you might be like, okay, well, what is a quasi-polynomial? For maybe you've never seen a quasi-polynomial. So a quasi-polynomial is a function, let's say from z to r of this form, again, where instead of coefficients, we have periodic functions. And then you might say, Andrés, you kind of just repeated the same thing you said before, and that still doesn't help me with the definition. So here's an alternative definition that I kind of prefer. And so I kind of think about this as a piecewise function where each of the pieces are functions depending on my period. And so each of these f's of I are in fact polynomial. Okay, and so it kind of cycles through after some period. Okay, and we'll see an example of it in just a bit. And equivalently, we put the Ehrhart quasi-polynomial in a generating function. And so I'm going to define, we could still get a nice rational form again. Actually, I've been using my cursor and I can't see, I don't know if you can see my cursor when I'm circling. Okay, good. And so I'm still going to call this numerator the H star polynomial, but in this case, it's a polynomial of degree less than q times the quantity d plus 1. And now you notice that this denominator business is popping up in here. And I will say also that I'm not writing this in lowest terms, okay? So it might be that you could simplify this, but I'm not going to. I just really want to keep this nice rational form, okay? And so let's do an example. So let's take just a small example of this polytope P to be the convex hull of these 4 points. And maybe if you're good at visualizing this, you can tell me what it is. And I'll give you some time to think about it. And you should probably see that it is a rectangle. And so it's this rectangle that I've drawn here. And I like to say in like my 4th grade level drawings. And I also like to say there's some charm to drawing it by hand. So I kept my drawings instead of tick-zing them. But here is that rectangle. And notice that it is a rational polytope. Again, these are exactly the vertices and they're rational points. But I still care about enumerating the number of lattice points. And in this case, I have 3 lattice points in my polytope, okay? And I take integral dilates of these things. And so here's 2p, 3p, 4p. And so I said the denominator is the least common multiple of all vertex coordinate denominators. So in the LCM of my vertex coordinate denominators here will be 2. So we should expect that this should have period 2. And I should say that when we're talking about Ehrhart quasi-polynomials, sometimes polynomials will exhibit a phenomenon called period collapse, meaning sometimes like you expect the period here to be 2, but sometimes the polynomial will have period 1 and it turns out to be a lattice or just a polynomial. But in this case,
but
it turns
Andrés,
out
can I ask something for a clarification? The period collapse, it doesn't mean that what you started with was an integer polytope or somehow equivalent to an integer polytope, or does it mean that?
No, it could be a rational polytope. It's just in some way it could have smaller period than we would expect, right? So like we expect the period to, for the most part, be the denominator, but it might be like if my denominator was 5, my Ehrhart quasi-polynomial might have only 4 polynomials showing up. And so it might be just cycle through 4 polynomials. And that's a big field, there's a lot of work to be done in that area. But in this case, in this particular example, it did turn out to be period 2. And so we only care about whether our dilated is even or odd. And so you might see, okay, well, look at this one. That one should be some, if you know about Ehrhart polynomials, one way to kind of check if something is an Ehrhart polynomial, or kind of like in my checklist, is that the constant term is always 1. Yeah. And so in fact, this one is an Ehrhart polynomial, and we see it's actually the Ehrhart polynomial of 2p. Yeah. Okay. But again, this one only cares whether my dilate is even or odd. And then I run it through my generating series, and here's what it looks like. And then there's a lot of questions to be asked, right? About the H-star polynomial. I mean, we notice, like, what's something that you notice about this one? Maybe just looking at it, you see, oh, it's palindromic. And so I'll hopefully give an answer to that. I always say that I'll give an answer to it, and I always forget. So please hold me to it as to maybe why this is happening in this particular example. Okay.
So Andrés, I have a question too.
Yeah.
So do you know in general ahead of time if there's going to be a period collapse or not? Or like?
So for the most part, no. And I think it's that, and one of the reasons I say why it's a big field is because as far as I know, period collapse has been studied for very small dimensions. So I know that like Terrell McAllister at Wyoming and some of his students have done things for like polygons that exhibit period collapse, but there's not much more. I think there's like maybe at most 5 papers out there that I've read on period collapse, which I don't know if 5 is a lot or a little, but I feel like it's a little, especially since, you know, there's a whole bunch of papers on Ehrhart theory.
So I'm just can I ask you another question? So the sum of these coefficients, so yeah, can you say something about the sum of the coefficients at the end? Of the numerator?
Yeah, so in the lattice case, the sum of the coefficients in the H-star polynomial is exactly the volume, and that's not that's not true in the rational case. So I guess there's not much more to say about the sum of the H-star polynomials, but hopefully, like in one of my results, you can get at least some interpretation, some combinatorial interpretation of them. Yeah.
Does that mean the coefficient of the highest degree term, they're not always the same when the degree is like bigger than 2?
Sorry, can you repeat that?
Yeah, so when you have a period that is maybe bigger than 2, can you say for sure that the coefficient of the highest degree term, are they all the same?
Oh, so yeah, so if you like look at this, for example, I guess maybe in the future I should start doing something bigger than just period 2. But in like the way that this works is like I'm kind of encoding each of these parts in each corresponding part, like whether it's even or odd. But if we had multiple parts, that means that I'm having, you know, 3 things that I'm summing over. And so each of these numerators are only seeing coefficients, exponents that are T mod, in this case, it would be T mod 0, and then this would be T mod 1, right? But if I had period 3, it would be T mod 0, T mod 1, and T mod 2.
But in the top, for example, both of them start with 2. The leading term of both is 2.
I see. Oh, in the Ehrhart quasi-polynomial, yeah, the leading coefficient will always still be the volume. That's right. Yeah, I guess I was misunderstanding the question. Yeah, but yeah, the Ehrhart, the leading term of each of the period, the parts of the period, the parts of the quasi-polynomial would be the volume. Yeah. Awesome. Yeah, these are all great questions. So please continue asking them. And so in part due to Ehrhart and mainly due to Ian McDonald in the 70s is we have this concept of combinatorial reciprocity for rational polytopes. And so if you substitute, or if you plug in some negative t into my Ehrhart polynomial, we get this relationship where we can count the number of integer lattice points in the interior of the polytope up to a sign. Okay, so this is again, in part, like it's one reciprocity theorem that falls into a lot of combinatorial reciprocity theorems. And so here's the equivalent statement for the Ehrhart series. Okay. And in the 80s, Richard Stanley proved that the coefficients of the H star polynomial are in fact non-negative. So that's quite nice. And I hope that I'll illustrate a different way to get Stanley's results from one of our results. Also due to Richard Stanley from 93 is this monotonicity result that, I mean, some of you might have seen, but I feel like maybe it's not as popular as some of the other Stanley results in Ehrhart theory. But what does this result say is that if you have a smaller polytope contained in a larger polytope Q, where you can dilate both of them and so again, P and Q are rational polytopes. If I can dilate them to be big enough by some integral value Q, where they're back to be like both of them are now integral, then what does Stanley's monotonicity result say? It says that the coefficients of the H star polynomial of Q dominate the coefficients of the H star polynomial of P. And so I'll have an example of that later on. And so maybe I'll tell you the goal and then we'll take the 5-minute break, right? That's the way the goes. So I'll tell you what I hope to tell you in the later half of the talk. And so I want to present a generalization of a decomposition of the H star polynomial for lattice polytopes that's due to Betke and McMullen from the 80s. And I want to use that decomposition to provide another proof for Stanley's monotonicity result. And so in fact, actually, Betke and McMullen's decomposition of the H star polynomial gives non-negativity for the lattice case. So that was already kind of known, but you know, we're not piecing the pieces together. And then I also want to present a generalization of the H star polynomial for lattice polytopes due to Stapledon, and I'll show an application of this decomposition to end. Okay, and so then I'll stop here and we'll take the 5-minute break.